So one way to know what is oxidized and what is reduced is to actually write out the half reactions and see what was gaining and what was losing electrons. But it can often be much quicker just to use this number line and say if it became more positive, if the oxidation number increased, then the thing was oxidized. If it became more negative, then it was reduced. So in order to use this number line, though, you need oxidation numbers, which are represented on that number line. And so let's talk about what oxidation numbers are and the rules for calculating them. Oxidation numbers can be charge. If there is a charge on an ion of a monatomic element, then that charge is the oxidation number. But sometimes also some things might be part of an ion, and so they might have some covalent bonds, and so they might not have an ionic charge, but they have something like a charge, which is oxidation number, which presumes electrons might go all the way towards the most electronegative element. Okay, more complicated than we need. Let's see how to calculate oxidation numbers. All right, anytime you see a free element, so a pure element that has no charge on it, then its oxidation number is 0. So for example, if you see pure oxygen or pure chlorine or pure copper, if you see no charges and no other elements next to them, then their oxidation numbers are 0. Second, if there is an ionic charge on something, then the ionic charge is the same as the oxidation number on it. So anytime there is a lithium ion floating around or stuck to some negative ion, then it has a +1 charge. You know that lithium has a +1 charge because it's in group 1A. They tend to lose 1 electron to get a noble gas configuration. And so that +1 charge leads to a +1 oxidation number. Similarly, calcium is in group 2A. If it's an ion, then it has a +2 charge, and so it has a +2 oxidation number. Chloride in group 7A. Those tend to gain 1 electron to get a noble gas configuration. So they get a negative charge and a -1 oxidation number. But like, if you had phosphide, group 5A, they tend to gain 3 electrons to have noble gas configuration. So they might have 3- charge and hence a -3 oxidation number. Also, most of the time in this class, if you're not dealing with pure oxygen, then oxygen next to anything else is going to have a -2 oxidation number. Exception, it would be -1 if there's an OO single bond, which you might find in a peroxide, like hydrogen peroxide. This is a memorized one. Oxygen in this has a -1 oxidation number, but pretty much most of the other times, oxygen has a -2 oxidation number. Hydrogen is generally +1 if it's next to something else, but it's -1 if it's bonded to a metal. So in water, the hydrogen has a +1 oxidation number, but if hydrogen is next to a metal, then the metal might have a positive charge, and so the hydrogen might have a negative charge. That's how they might stick together. And so, hydrogen next to a metal, a hydride, is -1 oxidation number. If fluorine is next to something else, it's -1. And then finally, sort of very importantly, this is the equation to show how the charge of an entire compound or ion is derived. It comes from the summation of the number of atoms of each element times the oxidation number of those elements. So that summation, add them all up, that summation results in the substance's overall charge. And so, let's use all that to calculate for the oxidation number of this phosphorus in diphosphorus pentoxide. So, the number of phosphorus atoms, 2, times the oxidation number of it, oh, that's what we're looking for, I underlined it, plus the number of oxygen atoms times their oxidation number, minus 2, that all adds up to 0 because there's no overall charge shown for this species. This is a compound, not an ion overall. All right, so where did this -2 come from? Remember, oxygen is -2 if it's next to something else, except when it's in a peroxide. Okay, so we have 2x plus 5 times -2 is equal to 0, or 2x minus 10 is equal to 0. Solve for x. X is plus 5. The oxidation number of phosphorus is positive 5. Wait a minute, I thought phosphorus, which is in group 5A, would get a -3 charge? Yeah, like phosphorus gets a 3 minus charge if it's an ion, if it's next to a metal, if it's a monatomic ion. But turns out phosphorus can have many different possible oxidation numbers, not charges, depending on how many oxygens nearby, for example. So in this case, it's plus 5. You actually have to calculate these. All right, second, we have phosphite. So here, there's one phosphorus of unknown oxidation number. We're looking for it. I underlined it. And there are 3 oxides of -2 oxidation number. And they all add up to an overall charge of -3. That's seen here with the overall charge of this polyatomic ion. And so arrange for the value of x, it's plus 3. Yes, phosphorus was plus 5 in the earlier case. It's plus 3 in this case. These non-metals, a lot of them can range from like plus 7 to like -5 or so. There's a large number of possibilities. You have to calculate them. Okay, let's say that we have lithium sulfate. Find the oxidation number of the sulfur in there. All right, so there's 2 lithiums and they're stuck to sulfate. And so the only reason that they might be hanging out near this negative ion is because they have a +1 charge. So yeah, lithium is in group 1A. It gets a +1 charge if it's an ion. And then there's also 1 sulfur of unknown oxidation number, and then there's 4 oxygens of -2 oxidation number. That all adds up to 0. So solve for x, and it's plus 6. Now try iron 3 nitrate. Why is it called iron 3? Well, that's kind of found by seeing what charge it might have, which would give an overall charge of 0. You see, this whole thing has a charge of 0, so all the oxidation numbers or charges of things need to add up to 0. This goes back to 10th grade chemistry. 1 iron of unknown oxidation number plus 3 nitrates. Each one is -1 charge. You know that because NO3 is -1 on the polyatomic ions list. All that adds up to 0. So you solve for x, it's plus 3. Now if you wanted, you could actually use oxidation numbers in here. You could solve for the oxidation number that nitrogen must have in nitrate. Solve for this given all that. And you would see nitrogen would be plus 5, and then you could also account for 3 -2 oxygens, and it would give you all the same calculation, or at least a result. Okay. So we now know how to use oxidation numbers. Let's see how to actually, use them to determine what is oxidized or reduced. So this is kind of like the quicker way to determine what is oxidized or reduced, instead of actually writing out whole half reactions. All right, so identify what is reduced in this reaction and what is oxidized, right? So one way to do this is to look at the oxidation number of fluorine. It's pure fluorine. It's not next to anything. There's no charge shown, so it's an oxidation number of 0. But at the end, it must be -1. Anytime fluorine is next to something else, it's -1. So going from 0 to -1, becoming more negative means it is reduced. That is because it gained some negative electrons. Gaining electrons is reduction from the last video. And then also you can take a look at bromine. It was -1. You know this because it was next to Na, which was +1. And so it then turned into 0 oxidation number. That was pure bromine, elemental bromine. So it went from -1 to 0. It became more positive. So that is to be oxidized. So boom. I mean, you could kind of solve this without even writing out any algebra or writing out any half reactions. Okay, so if I just asked you what is reduced, you'd say fluorine. But if I said what is the oxidizing agent, you would say fluorine as well. Remember, if something is reduced, opposite, it's the oxidizing agent. And then sodium bromide. The bromide within it is oxidized, so the sodium bromide is the reducing agent. All right, last problem. This one's a little bit more complicated. So you take some sodium thiosulfate and it reacts with iodine to provide sodium iodide and this compound. Identify what is oxidized and what is reduced. All right, so the quick thing is to look at iodine. It went from 0, because it's elemental iodine, to -1. It must be -1 because it's next to a positive sodium. So it was reduced. It became more negative. Boom. Iodine is the oxidizing agent. But another thing you can do is actually solve out for the oxidation number of some of the elements in here. So, sodium is next to something before and after. It's going to be +1. Oxygen is next to something before and after. It's going to be -2. So sodium and oxygen don't really change, but sulfur can have many different oxidation numbers, like many more complicated nonmetals like phosphorus and sulfur and, arsenic. Sulfur, figure out its oxidation number before and after, and that will tell you whether it's oxidized or reduced. So at first, it was next to 2 sodiums, each was +1, and there were 2 sulfurs of unknown oxidation number, and there were 3 oxygens of -2 oxidation number, and that all added up to 0. There was no charge shown for this overall compound. So you solve for X, and it's +2. But then later on, sulfur again, there were 2 sodiums of +1 oxidation number / charge. There were 6 oxygens of -2 oxidation number, and there were 4 sulfurs of unknown oxidation number. That's the one that changes, sulfur, or phosphorus, or arsenic, or chlorine, or bromine, or iodine. And just non-oxygen. That one doesn't change very much. Fluorine doesn't change. All right, so you solve for X, and whoa, it's not even a whole number. It's 2.5. All right, so you see that sulfur goes from +2 to +2.5. It became more positive. So going up, it must be oxidized. Hence, sodium thiosulfate is a reducing agent. That's all on that one.